तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 23 on the series on mechanical measurements. Towards the end of the last lecture, we were in fact looking at the measurement of displacement, which is the result of a pressure being applied on a diaphragm or a bellows type of arrangement, and this displacement is measured using what is called a linear variable differential transformer, or for short we call it the LVDT. So, we just started looking at the theoretical functioning or the theory behind the functioning of the LVDT. What we will do is to continue that discussion, and we will also look at what is used as a practical LVDT circuit, and then let us take a look at gauges which depend on the capacitance between two electrodes. The space between that is filled with an dielectric, and the distance between the two electrodes, if it changes, it gives rise to a change in the capacitance, and this change is brought about by the application of a pressure. For example, it could be a diaphragm gauge, which basically is a capacitance type transducer. So, we will look at the principles and circuitry appropriate to that, and then we will close the discussion on the different types of pressure transducers by taking a look at a simple example, which is a diaphragm gauge example. I call it example 24. If time permits, I will look at the transient response of pressure transducers. So, the thing we are going to do is to look at the LVDT theory and practical circuitry, look at the capacitance gauge, how it works, and then the example, and then we will try to see if we can do something about transient response. This is really a sketch we already have seen in the previous lecture. Just to recapitulate, I have an LVDT is essentially there is a primary coil here, there are two secondary coils, and there is a core which is capable of moving up and down, and this is the one which moves with the pressure transducer, gives rise to a movement of the core either in the downward direction or the upward direction, as the case may be. This primary coil is energized using an AC, a high frequency AC, usually for several kilohertz. It gives rise to two voltages on the secondary coil, V1 for the coil up here and a V2 for the coil down here. These are two AC voltages which are going to come out, and in fact, if we are able to measure the difference between these two AC voltages by putting the secondaries back to back, you see that the output voltage is V1 minus V2. This V1 minus V2 is going to be proportional to the displacement of the transducer of the core, and of course, this displacement has come about because of the pressure being applied in the pressure transducer. There are some drawbacks in just measuring the difference between two voltages. We will look at it a little later, but for the present we notice that the output voltage here will be 0 if V1 and V2 are equal, when the core is symmetrically placed with respect to the two secondary coils. If the symmetry condition is disturbed, you are going to get an output here. If the coil moves, the core moves upwards, the secondary one will produce a higher voltage compared to the secondary 2, and therefore, this will be a positive AC signal, and if the core moves downwards, it will be exactly the opposite. So, the phase of the output V0 with respect to the phase of the primary excitation voltage depends on whether V1 is greater than V2 or V2 is greater than V1, as the case may be. This particular circuit is not adequate for practical purposes. So, we will see how a practical circuit can be made, which is going to be helpful in measuring the signal. So, before we do that, let us look at the output which we are going to expect. Just whatever I said in terms of words, I have repeated here. The output of an LVDT excited by an AC supply. So, we have the output, either it is positive, on this side is the positive output, on this side is the negative output with respect to x equal to 0. There is a change in the phase, that is what is important. The phase angle changes from 0 to 180 or minus 180 in this case, when you change the displacement from this side to this side. But essentially it is a linear output which follows a relationship shown by this red straight line, either on the positive side or on the negative side. The practical circuit, we will have to look at a few other things. In fact, toward the end of the last lecture itself, I mentioned in very brief about the practical circuit, but I think we will look at it more carefully now. So, I am just showing a block diagram of LVDT signal conditioner. Signal conditioning means that a transducer is producing some effect which is in the form of either a current or a voltage, and this voltage is the magnitude of the voltage or the magnitude of the current may be very small, in which case we will have to condition the signal. It may be in the form of AC signal, in which case I would like to make it into a DC signal, for example. So, signal conditioning in general means many things. It may be amplification, that means that you are going to increase the magnitude of the output to make it readable by using a simple meter. It can also mean that you are converting it from AC to DC, that is what I call as demodulation. So, amplifier plus demodulator, this is what is on the secondary side. As you can see here, there are two secondary windings, two secondary voltages are going to come out. The sine wave reference is going to drive the primary through a power amplifier, because the primary requires a large current, in which case the power amplifier is required because it has to drive the current through the circuit, and the two secondary voltages which appear here are in the AC form, alternating form, just like the input waveform, because the transformer is an AC instrument, it will magnify AC voltage or modify the AC voltage applied on the primary and give rise to a secondary AC voltage. So, the difference between these two is what I am interested, but I want to first convert it to a DC signal by demodulation and then use a filter to remove the ripple, and then you get a DC output which may be either positive or negative depending on which way the core has moved. If it moves in one direction, it will be a positive value here. If it moves in the other direction, it will be a negative value. Let me just briefly look at how this can be accomplished by giving a simple schematic of a circuit which can be used for this purpose. So, I have the AC input, I am showing in a schematic way here. The AC input is between these two terminals, which are the primary terminals of the LVDT. The LVDT is here in a block fashion. It has got two outputs, one across the top coils and the other one across the bottom coil. I am assuming that the middle one is ground, this is ground here, and therefore, there is a voltage appearing here, AC voltage appearing here, which I call as AC output number 1, and there is an AC output 2 appearing at the bottom. I am using two diodes. This diode will make it is a half wave rectifier. You will have learnt about half wave rectifier in your electrical engineering course. So, you know what I am talking about. The output on this side is going to be one sided, because it is a demodulator. That means, it is going to remove one part of the wave, either the lower part or the upper part. So, what I get here is a DC voltage or a wave which is going to go only in the positive direction or the negative direction, similarly here. And if I am using these two in opposed fashion, I will get the top going wave here and the bottom going wave here, and this is the filter element. This filter is going to remove the AC component, and the AC component will actually go to the ground, and the DC component will appear across the output here. So, it is a very simple arrangement where I have two half wave rectifiers, one for the output across the coil number 1, another for the output across the coil number 2, and then I am going to use a filter and then get the DC output. So, you have AC input coming here, if necessary through a power amplifier, as I indicated earlier, the LVDT, and the LVDT gives two outputs. When there is a movement of the core with respect to its null position, then either this voltage or this voltage will be higher, and accordingly the DC output will show either a positive or negative sign. Actually, what I am going to do is going to show a better way of doing it by using a full wave rectifier. I will do that on the board, and let us look at how it is going to be appearing. So, what I will do is I will just show one of the secondary coils. Let us say secondary 1, and it will be similar for secondary 2. The secondary coil is here. This is secondary coil, and we are going to connect a full wave rectifier bridge as the demodulator. So, I am going to have 4 diodes shown you will have to wait to understand what is happening here. I will describe the physical working of the circuit, and I have a load resistance across that. So, the voltage is actually picked out across this. Output, let me call it as output number 1. Similarly, for the secondary coil number 2, I will have exactly the same kind of thing at the bottom. Okay, this is the output of the top one. So, if I look at the output, AC output 1, it will show something like this. This is output number 1, and what comes out as output here will be full wave rectified. So, I will get something like this. Okay, this is the full wave rectified. Rectified means it is on one side only output, and this magnitude here we will call it as V maximum, V1 m or V1 maximum. This will depend on the core position, function of the core position, function of the core position. So, if you look at this thing, if the AC wave is coming here, if this is positive with respect to this diode will conduct, this diode will conduct. So, the signal will pass through like that. Okay. If this becomes negative and this becomes positive, the other 2 diodes are going to do the conduction. So, that is why the output is going to appear for the first half cycle. This corresponds to this, I will say T by 2, this corresponds to this T by 2 here, and this will correspond to this half cycle, this will be T by 2. So, something like this. So, this is actually, this portion has become this portion now, it has been inverted or rectified. So, that is what the full wave rectifier is. In the sketch which I showed during in the slide, I would not have, for example, what I would have had is if I had only half wave rectification, the alternate ones will be missing, these will be missing. So, if I pass this wave through a filter which is going to remove all the high frequency component, what you will get is you will get the mean value only will come through, the mean will pass through. So, the average value will be something like this is the average, or the V1 I will say DC, V1 DC is going to pass through, the rest of the thing is going to be removed. So, now let us look at the way it is going to look when you look at both the. So, you have V1 DC, this is coil 1, and coil 2 will give you V2 DC. This is the second coil. So, if I take the difference V 1 DC minus V 2 DC, this will be your output for a given displacement of the core. So, if the displacement is more towards the coil number 1, that is away from the null position, it goes more close to the coil number 1, this will be greater than this will be positive, and if I have a displacement in the opposite direction, I will get a negative. So, this voltage will change sign, and if you remember what I showed in the figure earlier, you had a linear variation both the for positive as well as negative displacement of the core, and this follows a linear relationship as was indicated there, and this voltage is proportional to the pressure difference, and the pressure difference has given rise to a certain displacement which is a linear relationship. Therefore, this voltage difference between these two is a function is proportional to the pressure difference. So, we will say that this V 1 DC minus V 2 DC is proportional to delta P. This is the important thing. Now, let us look at a slight improvement in this circuitry. Suppose I have a V 1 DC, V 2 DC, and how does it come about? It comes about because we have a V input AC. The magnitude of V 1 DC is proportional to V input AC. So, if AC input for some reason changes slightly, this will change, because a transformer, if you apply a little higher larger voltage on the primary side, the voltage on the secondary side is going to follow it. It is going to increase slightly. If you decrease it is going to decrease slightly. So, if I do the following, if I take V 1 DC minus V 2 DC and divided by V 1 DC plus V 2 DC, if it is proportional to input AC signal, all these are going to increase by the same or decrease by the same fraction. Okay. So, you see that this is independent of input AC magnitude. This ratio, the difference between the voltage V 1 and V 2 on the DC side, divided by the sum of these two, or the average proportion to the average of the two, this is independent of the input AC magnitude. That means, even if the input AC signal changes slightly either on the higher side or the lower side, it is not going to make any difference. Therefore, normally what is done in the circuitry is to measure this. This is what is indicated. This is what is measured. So, we have to take the sum and the difference, then combine together to get the voltage. So, I am not going to show the complete circuit, but what I will do is I will just show what is going to happen now. From the coil 1, I have got this, coil 2, I have got this, depending on the, this is V 1, this is V 2, DC, because I have rectified or demodulated, and I am going to pass it through a filter. So, what I will get is a voltage like this. This is V 1, you remember I said maximum, and this will be, I think I will just change it slightly here. This will be here. This is V 2 maximum, and the what you see here is the difference between these two. So, it will be either a small voltage, this is the positive, this is V 1 minus V 2. Okay, the difference is going to appear. I can also have another channel through which I calculate the V 1 plus V 2. So, we have V 1 minus V 2 in one channel, V 1 plus V 2 I can have another channel, and then take the ratio. It is called the ratio amplifier. You can take the ratio of the two signals. So, this is basically what is going to be done in the case of LVDT transducer, which is connected to a pressure transducer. The pressure transducer is going to communicate the change in its or the displacement, which is due to the pressure difference. It is going to communicate to the core of the LVDT, and the core of the LVDT is going to create two AC voltages. These two AC voltages are demodulated to get two DC voltage outputs. They are filtered to get only the mean values, and these mean values are subtracted in one channel, added in the second channel, and the ratio is taken, and the ratio is now independent of the variations in the input voltage. That is the basic reason why we want to do this one. This is going to give you a signal which is going to vary with the delta P. So, with this we will now look at a different type of pressure transducer, and I will go back to the presentation in the form of a slide here. I am showing a capacitance pressure transducer just to indicate the nature of the capacitance transducer. It essentially consists of a diaphragm, as is indicated here. This is only one schematic. The actual pressure transducer may not look anywhere like this. It is just to explain the basic principle of the capacitance pressure transducer that I have written like this. There is a diaphragm, and there is an anvil which is fixed, and there is a small gap between the diaphragm and the anvil. Usually the gap is very, very small. I have shown a very large gap here for clarity. The gap may be much less than a millimeter, It is a very small gap talking about. And also remember, the diaphragm is going to undergo a very small displacement. It is not going to displace too much. It is going to be a very small displacement, as we have already indicated earlier. So, this variable gap, the gap between the diaphragm and the anvil, is full of some dielectric. In this case, most cases it may be either vacuum or air, and the capacitance of this, if you treat the diaphragm as one of the electrodes and the anvil as the other electrode, there is a capacitance between these two. There is a capacitance between the two electrodes, and this capacitance is a function of the gap, and the gap is dependent on the pressure, because the pressure, if you increase the pressure, it is going to, diaphragm is going to displace, and you are going to get a gap is going to reduce, and the capacitance is going to change. So, the capacitance pressure transducer changes the pressure to a displacement, and the displacement is going to create or change the capacitance of an element, in this case between the diaphragm and the anvil, and this change in capacitance I am going to measure, and if I measure the change in capacitance, I can now go back and say that the change in capacitance or the change in capacitance is proportional to the delta P which gave rise to it. So, the pressure is influenced or inferred from the measurement of the capacitance change, which is a consequence of the change in the position of the diaphragm, or the change in the displacement, or the change in the shape of the diaphragm, that gives rise to a displacement, and that gives rise to a change in the capacitance. Therefore, the capacitance change and the delta P are related to each other. Before we come to this, let me go to the board and indicate a few things. Let us look at the basic theory of the capacitance transducer. It is not very difficult to understand. So, we look at the basic theoretical framework of the capacitance transducer. So, if you have a, for example, if I take a parallel plate capacitor, so you have two plates parallel to each other, and in fact I will indicate a few other things now. These are two parallel plates, plate 2, plate 1, these are conducting plates, and in between you have a gap equal to a distance d. We will say area is A, here area is also equal to A, and we have a dielectric in between. So, this gap is full of a dielectric. In most applications of the pressure transducer, it may be simply air, or it may be some other fluid which may be there. The different materials which may be present here change the capacitance of the capacitor actually, because of the property of the particular dielectric medium which is going to be present there. Before we go into that, let me just write an expression for the capacitance. We will say capacitance C is given by 0.0885 K times area by distance, where I have area A is in centimeter squared, T in centimeters, and C will be in 10 to the power of minus 12 farad or in picofarad. This formula is adjusted such that you get the result in the case if you substitute area in square centimeters, the distance between the two plates in centimeters, and there is an extra term here. This is called the dielectric constant. And let me just digress a little bit and look at what this dielectric constant is. This is the ratio of two things. It is also called the ratio, dielectric ratio. So, any medium is characterized by what is called the permittivity. And the usual symbol used is epsilon. And if it is vacuum, it is called epsilon subscript 0, and it has a value of roughly equal to 8.85 into 10 to the power of minus 12 farad per meter. This is the value. So, this is a known value for vacuum, and for air it is very close to this actually. For air also it is very close to this, and the value k which we have there is nothing but epsilon divided by epsilon naught. This is called the relative permittivity. This epsilon naught occurs in the fundamental law which gives forces between two charges. It comes from the equation of electrodynamics. So, we will not go deep into the details of that. We just want to have just enough understanding of what we are doing. So, the k is a relative permittivity, that means it compares the value of the epsilon for the medium with epsilon naught for vacuum. And in fact, for a few materials I have I am going to just write down. So, the value of k for some materials and the K values. Vacuum of course is equal to 1 by definition. Air at 1 atmosphere, it depends on the pressure. This is 1.00059. So, that is why I said it is almost approximately equal to 1 for air, but if you increase the pressure to 100 atmospheres, it becomes 1.0548. So, you see that it is pressure dependent. A few other interesting cases, glasses, different types of glasses. It may go from anywhere from 5 to 10. Mica. I am giving these values for a particular reason, which will become clear when I discuss that. Mylar 3.1. For example, if you take a PVC 3.18 and so on and so forth. When capacitances are made in practice, we use different dielectrics, and you can see here the value of the capacitance is proportional to the dielectric constant multiplied by A divided by D multiplied by that 0.0885. So, if you want to get a larger value of capacitance, you fill the gap between the two electrodes with a material of higher dielectric constant. So, that is the reason why these materials are used. If you use a glass, for example, you can get about 10 times the capacitance. For a given area and the distance between the two plates, I can increase the capacitance by choosing the particular material which is used as the dielectric between the two electrodes. Mica 3 to 6. These are all mica capacitances are available in the market commercially. When you want to go and buy and use it for your circuit purposes, you can have a mylar capacitance with mylar or mica or PVC, things like that. The reason why we have this is because they are going to give you different values of the capacitance. For a given size of the capacitor, you can increase the capacitance by having a material like this. You can also see that air or vacuum more or less equal to each other, almost close to 1, and therefore, that is the lowest capacitance you are going to get with air as the medium between the two electrodes. Between the two plates, if you have air as the medium, it is almost like the minimum value which you will get for that particular size A and the gap D, you will get the smallest. So, let me just look at the equation again. Suppose I look at the equation, we have C equal to some constant 0.0885 K times A by D. Once you have chosen the dielectric constant or the material between the two plates, this is not going to, this is going to be a constant. Once the area is chosen, because in the case of the pressure gauge, area is fixed, this is fixed. So, we will in other words say that C is equal to some K1 divided by D, because all of these are constant. So, 0.0885 capital K multiplied by A I can call as K1, therefore, this becomes C equal to K1 by D, and therefore, the change in the capacitance, actually I can use logarithmic differentiation which we have been using earlier also. So, dC by C equal to minus D by D. So, maybe I should say Di, so that the differential symbol and the distance you do not get confused with each other, or I can write it as delta C by C, because we are going to talk about small changes in the value of Di divided by Di. So, this is just for distinguishing between the derivative symbol or the D here and the D there. So, this is your fundamental equation. So, the change in the capacitance with respect to the capacitance is simply the negative of the change in the delta d, the distance between the two divided by d. So, if the d decreases, the capacitance increases, and if d increases, the capacitance decreases, which is of course true. So, you can also see here the C itself is equal to A by d is in the denominator. If d increases, C will decrease and vice versa, and that means that the change in or the relative change in the capacitance is proportional to the relative change in the distance between the two electrodes with a negative sign. And if you remember, this is proportional to the numerator is proportional to delta P. In the diaphragm gauge, the diaphragm is going to undergo a change in the shape, and the magnitude of the deflection is proportional to the pressure difference across the diaphragm. And therefore, essentially what we are doing is measuring the change in the capacitance and relating it to the change in the pressure or the difference in the pressure. Let us look at a few typical numbers. If I take a simple example, if A equal to 1 square centimeter, and let me take d as 0.3 millimeters. I said we are going to have very small distance between the two plates. In fact, I can calculate the value of C, which is given by 0.0885. If I use air, K is almost equal to 1. So, I will just say 1 here, area is 1 divided by d is 0.3, so many picofarad. This will come to about 2.95 picofarad. It is a very small capacitance. We are talking about small capacitance. And if you look at the sensitivity of that, it is nothing but the rate of change of the capacitance with respect to the distance between them. So, we will say the sensitivity S is nothing but minus 0.0885 divided by, it is nothing but the derivative with respect to. So, this becomes 0.03, this should be 0.3 millimeter, I have to make it 0.03 whole square, this is the derivative. This will be in picofarads per centimeter. This comes to about minus 98.33 picofarad per centimeter. So, the rate of change of C with respect to the distance, the derivative. This is nothing but the, if you remember what we used to talk earlier about, this is the influence coefficient. Or it says how big is the change in the capacitance for a change in the distance between the two electrodes. So, this basically characterizes the particular diaphragm gauge. If we know the material, of course, in this case I have taken air as the intervening medium. If I know the initial gap between the two plates, this is the initial gap, and if this initial gap changes by a small amount because of the application of pressure, the change in the capacitance will be given by the expression S equal to minus 98.33 picofarad per centimeter. So, with this background, let us look at the circuit which we will use for measuring the capacitance change. I have given a schematic of a possible circuit for this case, and I have indicated here to the towards the left of the diagram, you have a chamber, essentially a chamber in the form of a cylinder, hollow cylinder, and we have the diaphragm right in the middle. This is the diaphragm, and one side of the cylinder is subjected to pressure, which is the reference pressure, which may be the atmospheric pressure, or it may be vacuum depending on the application. On the other side, I am going to apply the pressure which I want to measure. So, essentially this diaphragm is going to be subjected to the higher pressure this side and the lower pressure this side, or vice versa. So, there is a pressure difference across this diaphragm. So, this diaphragm is going to undergo a small displacement, and now I have got two fixed plates which are very sturdy, and which are going to not undergo any change in their position because of the applied pressure, and these two are the two electrodes now, two parallel plates if you want to call it. Okay, two plates here. Actually, there is a diaphragm plus the top plate forms one capacitor, the diaphragm and the lower plate forms the second capacitor. There are in fact two capacitances here. One of them is subjected to the reference pressure on one side, the other capacitance other side we have the higher pressure or the lower pressure which we want to measure. And the what is happening is, if the diaphragm undergoes a change in its position, it is going to reduce the for example, if it moves up, it is going to reduce the gap between the top plate and the diaphragm, and it is going to increase the distance between the diaphragm and the bottom plate. So, one of the capacitance is going to increase because this is going closer to that, and it is going farther from the lower one. So, the capacitance is going to decrease. So, you see that if there are two capacitances here, one capacitance is going to change the positive direction, the other one is going to change in the negative direction because of the displacement. And now I am going to connect the two plates to two capacitances here, one at the top and the other one at the bottom. This may be a variable capacitance. Initially, when the pressures are the same on the two sides, the reference as well as this side, there is no change in the position of the diaphragm, it should indicate null. That means, I am going to vary this capacitance such that these capacitance, top capacitance, bottom capacitance, this and this, which are going to form a bridge circuit, are all going to be in balance. And in fact, you can see here that I have connected across this an AC source. Usually high frequency AC is used for this excitation. So, what you get here is an AC output, just like in the case of the LVDT. The LVDT also we had a similar situation. Of course, it was because of transformer action, but here we have two capacitances which are going to be out of balance, and therefore, these two, the change in the top capacitance and the bottom capacitance because of the pressure difference across the diaphragm is going to drive this AC bridge out of balance, and therefore, it gives you an AC output. Actually, this AC output can be demodulated like what we indicate in the case of LVDT, converted to a DC signal. It may be amplified to finally give you an output which is proportional to the pressure difference across the two sides of this diaphragm. Okay. So, again you see that the displacement of the diaphragm has been converted to the change in the capacitance, and that has given rise to an imbalance in the circuit, and this imbalance is going to give you rise to an AC output. This AC output may be either directly measured or it can be demodulated and amplified to give you a DC signal. So, that DC signal is going to be proportional to the delta P across the transducer. So, that is the basic way the capacitance pressure gauge is going to be used. So, with this background, we have basically come to a close of our discussion on different types of transducers for use for measurement of pressure. What I will do is, I will take a simple example of a diaphragm gauge, so which I call as example 24. And let us look at the case of a diaphragm gauge. So, we are talking about a steel diaphragm gauge, a diaphragm made of steel diaphragm. I want to find out what is the size of this diaphragm, what is the thickness of the diaphragm required for a particular application. I want to measure, capable of measuring a maximum delta P of a maximum pressure of 7 megapascals. 7 megapascals will be something like 70 bars. It is a large pressure. Okay. So, we will assume that the steel material has a Poisson ratio of 0.285 and the Young's modulus E is 207 gigapascals. These are assumed for the material we have chosen for the diaphragm. So, the idea is to find out what should be the size of the diaphragm. If we are going to assume that the output required, this is the design requirement, is 2 millivolts per volt. This is the performance required at this particular pressure, 7 megapascals. Of course, when we are measuring a pressure like 7 megapascals, it does not matter whether we call it the gauge pressure, absolute pressure and so on, because the difference is very small. We are talking about very small difference between the atmospheric pressure and that pressure. There is a very large pressure, gauge pressure, absolute pressure, there is not much of a difference in terms of its value. Okay. Now, we will recapitulate whatever we learnt earlier. We talked about the performance of a diaphragm gauge. We gave some relationships. All I am going to do is to use those relationships to work out the numbers and in other words get some idea about what is going to be the requirement for a pressure gauge of this particular type. So, if you go to a manufacturer and buy a pressure gauge which is capable of 7 megapascals and this particular output in terms of 2 millivolts per volt, it is possible that the diameter, the thickness and so on will have been the numbers which we are going to talk about. So, we already gave an expression earlier. The output of the gauge in terms of millivolts per volt was given as 0.75. We just recapitulate P A squared 1 minus nu squared divided by E T squared into 10 to the power of minus 3. So, millivolt per volt. This is one equation which we already given earlier. We will also, this assumes that the gauge factor is 2. This gauge factor is for the measurement of the displacement is done by using a strain gauge, and the strain gauge has got a strain gauge factor of 2. So, this has nothing to do with the diaphragm we are talking about. This is something to do with the external specification which is already given to us. So, using the given data, what I can do is I can solve for the, in this case you see that there is a value of A is to be determined, T is to be determined. There are two quantities. This is the radius of the foil and this is the thickness. So, what I will do is I will fix one of them, or I will choose one of them to be a value which is reasonable, and then try to find out the other value, because both of them cannot be independently determined, one of them has to be chosen. So, I will choose the value of the diameter or the radius to be given, so that I can determine the other one. So, the value of A I am going to use as .5 millimeters, or the diameter is 17 millimeters. Okay. So, I will take the radius as 8.5 millimeters, plug in the value of A here. This P is nothing but the maximum pressure, which is 7 megapascals. So, all I have to do is to solve for T. So, for a 17 millimeter diameter diaphragm, we solve for T to get, this will be square root of 0.75, P is 7 megapascal, is 7 into the power of 6 pascals, A squared is 8.5 in 10 to the power of minus 3 whole squared into 1 minus 285 squared, this is the Pascal, the Poisson ratio, this whole thing divided by the E naught is 2, which is given as 2 millivolts per volt, multiplied by 207 gigapascals, is 10 to the power of 9. This whole thing gives you a value of 0.918 millimeter. So, the thickness of the diaphragm gauge is given by this quantity. So, we have a 17 millimeter diameter gauge, almost like 1 millimeter thickness. It is a very fairly thick diaphragm, because the pressure level we are measuring is also quite large. And let us find out what will be the central deflection. You remember, it is a diaphragm is held fixed at the periphery, and therefore, it is going to bulge out, and the maximum deflection occurs at the center, and we are now talking about the central deflection, which is given by 3 p a to the power of 4 into 1 minus nu squared, which was already worked out, divided by 16 E t cube. This formula also was given earlier in the last lecture. This will be 3 into 7 into 10 to the power of 6 into, this will be 8.5 into 10 to the power of minus 3 whole to the power of 4, 1 minus 0.285 whole squared, divided by 16 into 207 into 10 to the power of 9, 207 gigapascals. T cube is 0.918 into 10 to the power of minus 3 whole cube, and this comes to 0.0394 millimeter. If I represent it in the millimeter form, it comes to 0.03, and you see the thickness of the material is 0.918 millimeters. So, this is 0.039 divided by 0.92, which is very small. So, small deflection. Actually, this is the maximum deflection. The deflection is going to be smaller everywhere else. It is in the center of the plate that this larger deflection has taken place. The other deflections are even much smaller. And in fact, I can also calculate the natural frequency of this particular gauge, because it becomes necessary to know what is the frequency at which we can use it, because if you cannot work or operate the, if you are measuring a time varying pressure, you cannot subject this to a pressure which varies very close to its natural frequency, because it will damage the diaphragm completely. So, the natural frequency, we have already given the formula. All I have to do is to use the appropriate expression. This will be 0.469 T by A squared square root of E divided by the density multiplied by 1 minus nu squared. So, I will just plug in the values, 0.469 into 0.918 into 10 to the power of minus 3 divided by 8.5 into 10 to the power of minus 3 whole squared, square root of 207 into 10 to the power of 9 divided by, this will be 7830 is the density, 1 minus 0.285 whole squared. This will come to 31,948, 32 or 31 kilohertz. Obviously, the frequency will be quite large, because a small diaphragm. So, the you can see right here, if the thickness decreases, this will decrease, thickness increases, it will increase, and A squared is appearing in the denominator, the smaller the diaphragm, the higher the frequency. Therefore, you see that the frequency of this particular thing, the natural frequency of the diaphragm is very high. In principle, if I am going to use a diaphragm gauge of this type, I can probably subject it to a transient, which is probably half of this, or for example, up to 10 kilohertz or 20 kilohertz, there should be no problem in using this. So, the frequency at which it can be operated, if you are going to use it for measuring time varying signal, is partly determined by the natural frequency of the gauge itself. So, with this background, let us go back to the discussion on the electrical side a little bit, just to familiarize ourselves with the different types of transducer. Normal electrical input and output of pressure transducers are given here as a sort of to give an idea as to what we do in practice. The standard input is between 5 and 24 volt DC for amplified voltage output transducers, where you are going to get the output in terms of voltage. In many applications, we also use an output in the form of a current. This is especially in process applications. So, we use 8 to 30 volt DC as the input for 4 to 20 milliampere current output. Now, the question will be immediately asked as to how do we get a AC. So, obviously, when you use the DC voltage as the input, we have to have an oscillator or some such arrangement which will give you an AC excitation voltage in the case of gauges which require AC voltage. Okay. So, the standard input will be 5 to 24 volts for DC amplified, for amplified voltage output transducers, and for current type instrument 8 to 30 volt DC, and the standard output will be either 0 to 5 volts or 0 to 10 volt DC used in industrial environments, and in the case of process applications we usually use 4 to 20 milliamperes. So, let me just look at this 4 to 20 milliamperes slightly more carefully. If the voltage, if the current output of the instrument at the transducer is 4 milliampere, it corresponds to 0 or the minimum value of the pressure or whatever process parameter we are measuring. 20 milliamperes will correspond to the largest value which you can measure with that instrument. So, this is the maximum 20 milliampere, 4 milliampere will be the minimum, and if it shows 0, if the output current is 0, that means there is a damage to the instrument, that means there is some problem with the instrument. So, the way to recognize whether there is any problem with the instrument is to see whether it is giving 4 milliamperes when there is a delta P equal to 0 or not. If it is giving 0 for some reason, then you can immediately come to the conclusion there is some problem with the circuitry. So, I think we just had time to cover this much. So, what I will do in the next class or next lecture is to look at the transient response of various types of pressure transducers, and most probably it will be possible to cover the entire thing in the next lecture, and we will complete that. And transient response is very important in many applications. I will just show one or two reasons why we do that. Transient behavior of pressure measuring instruments is needed to understand how they will respond to transient pressures if the pressure is varying with respect to time. And sometimes measurement of transient or time varying pressure requires a proper choice of the instrument and the instrument parameters, and the coupling element which goes between the instrument transducer and the measurement point, that also needs to be looked into. So, from the first and the two reasons I have given here, it is necessary to understand what happens, how a transducer is going to behave when you have a time varying pressure applied on it. So, let us look at this in the next lecture. Thank you.